Hi, my name is Chima, and today I'll be solving Leetcode problem 257, binary tree paths. Alright, so for this question, we're given the root of a binary tree, and our goal is to return all root to leaf paths in any order. And it says here that a leaf is a node with no children. Alright, so let's break this question down. So first, we know that we're given the roots of a binary tree, so we're basically given a whole tree. And since the goal is to return all root to leaf paths, we need to figure out, starting from our root, what are all the paths that we can take to hit all our leaf nodes. So a leaf node in the tree is basically the node which doesn't have any subsequent children, so a node which doesn't have any left or right child. So for example, in example 1 here, the leaf node would be 5 here, and the leaf node would be 3. So since our goal is to return all root to leaf paths, one path starting from a root to the leaf will be 1, 2, 5. Another path starting from the root to the leaf would be 1, 3. And as you can see here in the output, the first path was path 1, 2, 5. The other path was path 1 to 3 as I described. Okay, and the constraint to say here is the number of nodes in the tree is in the range 1 to 100. So just a standard tree traversal algorithm should work for this. So when we traverse binary trees, there are a few different algorithms that we can use. So the two main tree traversal algorithms being breadth first search and depth first search. In this case, for this question, it would make more sense to use depth first search because they said that we want to find all root to leaf paths, meaning that we want to traverse deep first before we go wide, which is exactly what depth first search aims to do. So in regards to depth first search, there are three types of depth first search algorithms. There's pre-order traversal, post-order traversal, and in-order traversal. In this case, it will make most sense to do pre-order traversal, which means that as we traverse our tree, we want to be processing each node as we visit them, rather than something like post-order traversal where we process them after we fully explore the tree. So let's get started here. The approach is a little bit the approach is not very intuitive, but as I code and as I explain it will make more sense. But technically we want to build our path as we traverse the tree in pre-order fashion, and as we backtrack we want to eliminate the leaf nodes from the current path that we're on, so that when we explore further branches we can add new nodes to the current path that we're on, starting from roots. So that's the general overview. And as I said, we'll be using depth first search, which is a recursive algorithm. And yeah, let's go ahead and start solving that right now. So to begin here, I'm gonna have a helper method for helping me to do my depth first search. EFS, and this is gonna take roots, current path, all paths. Okay, and to begin, the base case with depth first search or any recursive algorithm is that we should first check if the root doesn't exist. So in this case, if we are not at a node, we just simply want to return. So if not roots, return. Then with pre-order traversal, as I was explaining, you want to process the node that we're on. So when we process a node, in this case, what we want to do is we want to add the current node to the path, to the current path that we're on. So we can simply do current path append string representation of root of all, because as you can see here in our output, we're looking for a string representation of the entire path. So once we append the value to our current path, we want to check if the node that we're on is a leaf node, right? Because if the node that we're on is a leaf node, then we know that we can, or rather that we've explored a root to leaf path. In that case, we can save this path to our all paths variable that we created here. So we need to check if the current node that we're on is a leaf node, as I just explained. So if not root dot left and not root dot right, could do all paths dot append. What we want to do, we want to join our current path by this forward arrow. Current path, right? And then if we're not at a leaf node, we just want to continue traversing our tree in pre-order fashion. So that means explore all of our left subtrees and then explore all of our right subtrees. So to do that, simply just use DFS, pass in root.left, current path, all paths. The same thing for our right subtree here. Change that to root.right, and then this is a very important step. After we've explored a specific path, as we backtrack up the tree, we want to pop. We want to pop the nodes that we've already visited in order to append other nodes which may lead to future root to leaf paths. So to do that, we just simply pop from our current path. So current path.pop. And once we're done with this depth first search algorithm, we need to utilize this. So in order to utilize this, we have an all paths variable here. So all paths is going to be an array of all the paths. Then we need to call DFS on our route that we're given in the example. The current path is going to be a dynamic a variable, like we don't need to store it in memory. Then for all paths, we just created that variable. Then after we're done, we just have to return all paths, and I believe this should solve the problem. Let's run it. So this passes both test cases if I submit it, and it works. So now let's explore the time and space complexity of this problem. So to begin, we know that we have a space complexity of O of n, as we're using an all paths variable here to store all possible root to leaf paths. And our recursive call stack, in the worst case, is also going to be O of n, right? Because like in the worst case, it can store up to n nodes, starting from root to leaf. Now, in terms of the time complexity, I would say the time complexity is also O of n, because we have to traverse all the nodes in the tree. And yeah, so time complexity O of n, space complexity also O of n.